I would like to hello everybody. Thank you for being there for our DinAmicI online seminar. So it's really a pleasure to introduce today's talk. So we have the pleasure of listening to Olga Bernardi from University of Padova and then Vincent Humilière from Sorbonne Universitè. We give a talk about recent developments on the Birkhoff attractor. So before starting, let me recall to everybody that we are recording the talk, and so we are streaming also on YouTube. So if you want to ask question, feel free to just switch on your microphone. But if you don't want, because it's on YouTube, just put your question on the chat, and then I will try to read it. So it's a pleasure to start with Olga Bernardi. So thank you for accepting the invitation, and whenever you want.
Okay. So thank you for to the organizers for this invitation. This is a twin seminar in the sense that both seminars, both talks are focused on the Birkhoff attractor, mine in particular on dissipative dynamics on the cylinder, and the one by Vincent about the generalization, recent generalization of this Birkhoff attractor. And so we start with the dynamics given by a conformally exact symplectic diffeomorphism with a fixed conformal ratio. This means that essentially it's an exact symplectic diffeomorphism, but it contracts areas in the cylinder, or more generally, to form on a general cotangent bundle. Moreover, we suppose that this diffeomorphism maps the strip, the finite compact cylinder S times -1 into its image, and is homotopic to the identity. A diffeomorphism with all these properties is usually called dissipative diffeomorphism. Since as a consequence of this dissipative feature, we expect, and in particular, we have, as a consequence of this property, the existence of a global attractor. I usually call this attractor Conley attractor, which is, since we start here from a compact, connected part of the cylinder, infinite cylinder, which is non-empty, invariant by definition, compact. And moreover, it separates, this is the global attractor, the cylinder into two invariant open sets. This open upper part and the other lower part. So the definition of Birkhoff attractor starts from the observation, the remark, that this global attractor is not minimal in the sense that it could be a priori further decomposed into smaller invariant sets. So to obtain the minimal with respect to the inclusion invariant set with all these properties, and moreover the property that it separates the cylinder, Birkhoff introduced this set, which is called Birkhoff attractor, which is given, one of the definition is given by the intersection of the closure of the upper part here and the lower part. So, in a sense, these whiskers are cancelled, okay, by this intersection. And if we consider this global attractor, at the end, the corresponding Birkhoff attractor is this one. So don't think that B is an attractor. It may be an attractor, but it's not necessarily an attractor. But it has all the previous properties of the global Conley attractor. In particular, with respect to the inclusion, it's possible with a simple proof, proves that is the smallest invariant compact connected set separating the cylinder. The first simplest example is the following dynamics, okay, where we have the contraction along the vertical fiber in the vertical direction. So at the end, the unique invariant set is the zero section, and the two attractors coincide with the zero section. Another popular example is the damped pendulum, here with the sign minus or plus, depends on the orientation of the vertical line. In such a case, the two attractors again coincides, but in general, depending on the straightness here of the dissipation, this attractor is not a graph, but has this form, which is exactly the closure of the unstable manifold of the hyperbolic point. So, question, what about in general the dynamical as well as the topological complexity of the Birkhoff attractor? In order to determine and give some sufficient condition to study this complexity, we need that the dissipative map is also a twist map in order to define two rotation numbers, the lower and the upper rotation numbers, which may coincide, but when they differ, gives information on the topological and dynamical complexity of the Birkhoff attractor. So suppose that this B is our attractor, which is not the simplest case, so when is not a graph, we can select the lower part, the lower graph here, so the points which are always where if we intersect with the vertical fiber, they are the last points of the unique point of the intersection from below, or the upper graph from above, okay? A sort of graph selection from the upper and from the lower. Then, when the diffeomorphism is also twist, we can define the corresponding rotation numbers by the usual definition of rotation number, and this definition is well posed since this limit converge uniformly on the upper and lower graph. The non-coincidence of these two rotation numbers gives information on the topological complexity of the Birkhoff attractor. So these ideas follow former ideas from Marie Charpentier and Patrice de Calvez, and a important theorem by Marie Charpentier proves that when we have a dissipative diffeomorphism, which is also twist, but all the cases, for example, for billiards, we have the twist condition. When the two rotation number differs, then the corresponding Birkhoff attractor is a so-called indecomposable continuum. That is, it cannot be written as the union of two compact connected non-trivial sets. To consider an example of such a set, consider, for example, this infinite intersection where we construct as follows. So we have this connected set, then we select this subset, and so on. And we proceed with the infinite intersection. We obtain a indecomposable continuum. The dynamical, the importantest, if you want, dynamical consequences on the Birkhoff attractor is that when these two rotation numbers differ, then each rational rotation number inside this interval is a rotation number for a periodic orbit on the Birkhoff attractor. And moreover, B contains an horseshoe, and the topological, the dynamics has positive topological entropy. So in literature, there are not lots of examples of dissipative dynamics, and in particular, the corresponding, the study of the corresponding Birkhoff attractors. So some years ago, we started to study the Birkhoff attractor for dissipative billiards in terms of the strengthness of the dissipation as well the geometry of the table. So we start to dissipate the Birkhoff billiard. In the general, in the case of the Birkhoff billiard, the well-known law is that the angle of reflection is equal to the angle of incidence. Here we measure the angle with respect to the normal in the tangency point, and in particular with respect to the sine of this angle. Okay, so we proceed with this discrete dynamical system. In the dissipative case, we contract, okay, the vertical, the momentum, if you want, okay, so S2 here, we contract with respect to the dissipative parameter A. So we apply the standard law and then we contract along the fiber. As a consequence, we obtain A sine of phi2. So this means that the velocity vector tends to the normal. And as a consequence, since two periodic orbits correspond in these coordinates to the sine of pi over 2, the sine of 0, which is 0, then two periodic orbits are not affected by dissipation and will play a role in the Birkhoff attractor, in the corresponding Birkhoff attractor. So the simplest case is when the Birkhoff table is a circle. By a theorem by Bialy, the circle is totally integrable. So the phase space is entirely foliated by invariant, not null homotopic curves. So the dynamics, the dissipative dynamics is the simplest one, and the attractors are equal to the zero section. The other simple case, if you want, is the ellipse, which is the integrable case for Birkhoff billiards. We describe this ellipse. We know that the ellipse has two periodic orbits, which are not affected by the dissipation. One is elliptic, the other, corresponding to the measure axis, is hyperbolic. And what happens is similar, if you want, to the damped pendulum. So the steps to obtain the Birkhoff attractor in this case is first proves that two periodic points belong to the Birkhoff attractor. Then that the first integral for the non-dissipative case becomes a Lyapunov function when we switch on the dissipation, whose neutral set is given by two periodic points. And then, with Anna and Martin, we prove that for the ellipse, the Birkhoff attractor corresponds to the global one and is given by the closure of the unstable manifold of the orbit for the hyperbolic point. Since these hyperbolic points are stable under small perturbations, the same holds when the table is close to an ellipse. But we can say more. So this is the general case. And in particular when the dissipation is mild, so close to 1. When the dissipation is strong, as expected, if you want, the Birkhoff attractor becomes a normally contracted graph, but we need an additional hypothesis, and in particular that the eccentricity is in this interval. Okay. So inspired by this toy model, if you want, we understood that in general, for general strictly convex billiard tables, we need to distinguish between strong and mild dissipation, and moreover, we need to notice, in order to apply the cone-fill criterion and obtain the normally contracted graph property. So we notice this geometrical assumption on the eccentricity. So what can we say in general for general strictly convex Birkhoff billiard tables? First, for strong dissipation. So the result is this one. The general geometric hypothesis for general tables, strongly convex. So here we assume that the curvature is never equal to 0, is that in every point of the table, the center of the osculating circle is inside the table itself, inside the interior, okay? And this correspond to this hypothesis in the case of ellipses. So the general theorem is that when we are in this special subset of strongly convex billiard domains, where we have this hypothesis, which we call the pinching hypothesis, and the dissipation is strong, then happens that the two attractors again coincide, as for ellipses, and this attractor is a normally contracted graph. The regularity depends on the regularity of the table. Moreover, for smaller dissipations, we can also decompose the Birkhoff attractor in terms of a finite union of closure of unstable manifolds corresponding to two periodic orbits of saddle type. Okay. For mild dissipations, we need to recall this important fact following Patrice Le Calvez. We can give information on the quality of the Birkhoff attractor by studying the non-dissipative dynamics. In particular, this is essentially a result by Patrice Le Calvez. We check and adapt the theorem for billiards. Suppose that the original diffeomorphism without dissipation has an instability region containing the zero section. So a region where we don't have invariant curve, not null homotopics. A region free of invariant curves. Then there exists a dissipative parameter such that if the dissipation is greater than this critical, if you want, dissipative parameter, then the Birkhoff attractor has different rotation numbers, upper and lower rotation numbers. So this means that the Birkhoff attractor is topologically and dynamically complicated. So when this sufficient condition is satisfied, guaranteeing this strange Birkhoff attractor, so I start from this first case. Clearly, when the strictly convex domain has a point of zero curvature, because in such a case, by Mather's criterion, all the phase space is free from invariant curves. So the phase space is an instability region, okay? Clearly containing the zero section. But this happens also generically, in particular for an open and dense subsets of strongly convex domains. And the idea is that if we have an invariant curve, not null homotopic, which is a Lipschitz graph by Birkhoff theorem, which passes through the zero section, it has a rotation number 1/2 and is fragile, in the sense that these curves can be destroyed by an arbitrary small perturbation of the table. Okay, now the idea was to study a model of dissipation also for the other types of billiard dynamics. So recently I studied, especially with Luca Baracco, the symplectic billiards, where the law is that we have here the first point, the second point, and the third point is given by the unique by strict convexity intersection of this line parallel to the tangent line in the second point. So in order to dissipate, to obtain a dissipative diffeomorphism, we need to introduce this a bit, if you want, strange model. So we fix the origin, and instead of considering the line passing through this point, parallel to the tangent, we consider the line passing through the point A gamma T1. Okay, so we contract this point in the interior. We obtain a genuine dissipative diffeomorphism, and so we can study the differences between the dissipative Birkhoff billiards. This model shares a lot of properties with the Birkhoff billiards, but with some specific differences. In this model, essentially, we don't have superperiodic orbits, okay? The orbits which are not affected by dissipations are 4 periodic orbits corresponding to parallelograms. Okay, so here a summary, okay? The simplest case for dissipative Birkhoff billiards is the circle. For the symplectic case is the ellipse, because with Luca we have proved that the ellipse is the unique, totally integrable symplectic billiard, totally foliated by invariant curves. But it's not the unique case where the Birkhoff attractor is very easy. Also, any centrally symmetric radon domain has the simplest Birkhoff attractor given by the zero section. Radon domains are centrally symmetric domains such that in any point of the domain, of the boundary, we can construct there exists a parallelogram of maximal internal area, maximizing the internal area. And these correspond to 4 periodic orbits, which are not affected to the dissipation. For this reason, radon domains usually play a role for symplectic billiards. The integrable case for Birkhoff billiard, as previously discussed, is the ellipse, which is the integrable case for symplectic billiards. It's an important open problem. Okay. Then for strong dissipation, if you remind, we have this subset of strongly convex domains with the pinching condition, with the osculating circle. In such a case, the 2 attractors coincide with a normally contracted graph. The same holds with the same technique for symplectic billiards, but in such a case without additional hypothesis, geometrical hypothesis. It's always true. For mild dissipation, the same result, so B complicated, is true here generically, and when the curvature is 0, for symplectic billiards generically, but for centrally symmetric domains, and also when the curvature is 0. In particular, the proof of this corresponding result, okay, wasn't so easy to obtain. So with specific differences. To conclude, we started also to study a dissipative version of outer area billiards. If I first introduced by Moser as also a model of planetary motions. Okay, so here the dynamics is outside the table. The phase space is the infinite cylinder. Here we have the zero section, if you want, corresponding to the table, and the law is that this distance, okay, between the first point and the second point is the same. So the tangency point is the point in the middle. Okay? To dissipate this model, we introduce that when we reflect, then this distance is A, R, not R. Okay. Simple properties. Here the conformal factor is A square. Okay, it's not a problem. And every point in the boundary is fixed clearly for every A. So every point in the boundary is not affected by the dissipation. So here the idea is construct the corresponding Conley global attractor, which may be this one, and then select the smallest invariant compact connected part. So if we do this selection, it's clear that in such a case, differently from the symplectic and the Birkhoff case, the Birkhoff attractor is always the table for every strengthness of the dissipation and is always also an attractor, in a sense that there exists a set whose omega limit is the Birkhoff attractor itself for every A. Moreover, when the dissipation is very, very strong, these whiskers here, where extremals are periodic points, don't survive. So since no periodic points, no periodic orbits survive, then the two attractors coincide. Okay? When the outer table is an ellipse, then this is the totally integrable case, and so the two attractors coincide for every A. The natural question is, what about the converse? So is it true that the two attractors coincide for every dissipative parameter only when the Birkhoff, the table is an ellipse? Okay, this question goes in the direction of Birkhoff conjecture, if you want, for billiards. Okay, so the answer of the above questions rests on the existence of non-degenerate periodic points for the initial non-dissipative dynamics. So as in Le Calvez setting, but from a different point of view, we need to first study the non-dissipative dynamics. And the idea is that if Psi1 has a non-degenerate periodic point, then it persists under perturbation. Then Psi for A close to 1 has a non-degenerate periodic point which produces a whiskers, and then for A close to 1, the two attractors cannot coincide. And this is true generically. So as a consequence, this is true that generically the two attractors do not coincide. So the open conjecture, perhaps not so easy, is that the two attractors coincide for every A if and only if the initial table is an ellipse. So finally, to fix the ideas, I would like to conclude to show to you some numerical experiments by Luca with Mathematica. So this is an outer billiard table with this polar equation without dissipation. So here we can have a periodic orbit escaping to infinity, but we need to increase, okay, we need to increase the iterations. So it seems that the dynamics is bounded, but it's not in general true, okay? Here, when A is very close to 1, many periodic orbits survives, okay? And the two attractors differ. Now we consider A smaller. It seems that only a 4 periodic orbit survives, given here these whiskers, okay? And finally, for smaller A, smaller dissipation, no periodic orbits survive, and in such a case, as predicted by the theory, the two attractors coincide. So I would like to thank for the attention and finish with these beautiful pictures. Thank you.
Thank you. Thank you a lot, Olga, for the great talk. Are there any questions or comments? Oh,
you have one. What's the difference between strongly integrable and integrable in the?
Totally integrable means
totally integrable, yes.
The whole phase space is foliated by closed invariant, not null-homotopic curves. So
Okay.
the simplest case, if you want. But for example, the ellipse for the Birkhoff dynamics is integrable, but not totally integrable. The unique totally integrable is the circle. Otherwise, if you draw the phase portrait for the ellipse, we can have also null-homotopic invariant
I see.
pairs of null-homotopic invariant curves. Okay.
I see.
So we have the existence of a first integral, which can introduce, I know, 2 or 3 ways, okay? But in the simplest case, the conserved quantity is the height on the phase space, okay?
Mm-hmm.
Otherwise, it's more complicated, and so it creates different level sets, which can be null-homotopic.
Okay, thank you.
I think the totally integrable was introduced by Bialy, okay, which usually studies these specific problems.
Mm-hmm.
Are there other questions? Or if not, I have a question, maybe very stupid, sorry. So you said that in the case of the outer billiards, when you do the dissipation, when you have the parameter, when you put a strong dissipation equal to close to 0,
yes.
you don't have periodic orbit.
Yes, it's possible with a not long, but it's possible to prove that all periodic orbits disappear. Yes.
Okay. Could you say something about why, maybe the intuition why they should disappear?
First is that when we introduce the dissipation, after some steps, it's possible to prove that the dynamics is inside a bounded region of the infinite cylinder. Okay,
Mm-hmm.
and then we use the compactness of this bounded region to prove that for a sufficiently close to 1, we have that all points converge to the table.
Sufficient close to 0?
To 0, excuse
Okay,
me. Yes.
okay, no.
Okay,
Oh.
so we use
Okay.
the first result on the compactness, okay, and then the strengthness of the dissipation.
Okay, thank you. So, and I have a second question, so maybe still very stupid, sorry. So you said that over here, what you get is that when you have if the Conley attractor does not coincide with the Birkhoff attractor, the whisker that you have are just like of periodic type, and why you cannot have something like a Cantor? I should probably know why, but
yes, maybe this is I draw this picture, yes, to fix the ideas that I imagine that these are, but not finite, maybe also in a Cantor set.
No, okay, it could
Yes,
be a
yes.
priori. Okay,
A
perfect.
priori, they may be in a Cantor set. I only use, because in my mind, to fix the ideas. Okay,
Perfect. Sorry, it was me who understand the.
Yes, yes.
Thank you so much. Are there other questions or comments? So if not, thank Olga again for the great talk. So let's continue with our DinAmicI seminar of today with the second part of our twin talk about Birkhoff attractor. So it's a pleasure to introduce Vincent Humilière from Sorbonne Universitè. We talk about higher dimensional Birkhoff attractors.
Thank you very much, Anna and Olga, and all the organizers in general. I'm very happy for this opportunity to speak. I was not aware of the existence of this group of friends, but great, apparently. Okay, so I will talk about the general problem, which is how to extend the Birkhoff attractor to higher dimension. And this is based on some joint work with Marie-Claude Arnaud and Claude Viterbo. Okay. And please interrupt me as much as possible, otherwise I will be very sad. So if you have questions, do not hesitate. Okay, so maybe a first question, if we want to extend the Birkhoff attractor to a higher dimension, is what would be the settings, the framework, so to which maps can we extend this? And so before in dimension 2, it was defined for maps which contracts the area. And so in higher dimension, a very natural framework would be conformally symplectic maps. Okay, conformally symplectic diffeomorphisms of a cotangent bundle. For me, it would be denoted by T star M. Okay. By conformally symplectic, what I mean is, so you know, on T star M there is a natural symplectic form which is denoted omega usually, and we will. So if the coordinates are denoted by QP on T star M, then omega is the differential of lambda, where lambda is PDQ. Okay. And a conformally symplectic diffeomorphism is just a diffeomorphism that contracts the symplectic form along this formula here. So there is a large class of examples which comes from Hamiltonian systems which are damped. So which means that we are picking Hamiltonian on the cotangent bundle, which is just a function on the cotangent bundle, which can possibly depend on time, but not necessarily. And we consider the usual Hamilton equations, so here. But we add some friction term here, this minus alpha p here. Okay. And okay, and if we consider the flow of such a system, which I will denote by phi h alpha t, then it satisfies the following equation, and we see that it contracts omega by a factor which is exponential of minus alpha t. Okay. So it's a very natural class of diffeomorphism to consider because it just comes from Hamiltonian system with friction. And so Olga talked already about the example of the damped pendulum. So here in that case, the equations are what I wrote here. And we can draw the Birkhoff tractor in that case. Remember, it was some... okay, it's not nicely drawn. Some infinite spiral like that, and then it goes back like this. So in that case, the Birkhoff tractor will look like this. Okay, and now back to our problem: how to extend to a higher dimension. It's really not obvious how to do it because you know, in the definition of the Birkhoff tractor that Olga gave. I don't know if I can draw some picture here. There was there was some picture like this in the Olga's talk with some strange things like this. Okay, and it was important in the definition that there is some upper part here and lower part there, and which were denoted by U plus and U minus, right? And then the Birkhoff tractor was the intersection of the closures of U plus and U minus. Okay, so the Birkhoff tractor was the closure of U plus intersected with closure of U minus. And so it's really important to have something that separates what's above and what's below. So in higher dimension, if you want this, somehow maybe the natural generalization would be to consider hypersurfaces instead of curves, because it separates between the lower part and bottom part. But in fact, when we consider the case of which is here, of a damped Hamiltonian, just in the special case where the Hamiltonian is 0, then in that case, the flow is just the Liouville flow. So it contracts everything to the 0 section. Okay? So I don't know for the what I just said here is that for H equals the 0 Hamiltonian, then if we consider the damped Hamiltonian flow, then this flow contracts everything to 0 section of the cotangent bundle. Okay, and so 0 section is definitely not a hypersurface, except in dimension 2. So it seems that hypersurface is not the right thing to consider to extend to high dimension. And in fact, from this example of the 0 section, what we perhaps see is that that the Birkhoff tractor should rather be some kind of Lagrangian submanifold, like the 0 section. But since we will want it to be not necessarily smooth, then we need something which will look like a generalized Lagrangian submanifold. Okay. Okay. We need really some generalized Lagrangians to be able to define the gamma support. So now I will talk about a way to define such generalized Lagrangians. And first I should probably recall what's a Lagrangian submanifold. So what will be useful for us, it's something called the spectral norm, denoted by gamma. But first of all, let me recall what's a Lagrangian submanifold in a symplectic manifold. This is just if I have a symplectic manifold of dimension 2n, then a Lagrangian submanifold is a submanifold of dimension n, such that the symplectic form vanishes on it. Okay. So I will give some example very soon. That's this, and these are really the most important submanifold in a symplectic manifold. I need another piece of definition is if I am in a case where omega is exact, so for example, in the case of a cotangent bundle, then we can say that a Lagrangian submanifold is exact if the restriction of lambda to L is exact. Okay, so since omega vanishes on L, then lambda should be closed on L. But to have a Lagrangian submanifold, for a Lagrangian submanifold to be called exact, we need lambda restricted to L to be exact. So here are some examples. First of all, notations. This I will denote this set of all closed exact Lagrangians in T star n by L, like this. Okay. Some examples. The most simple example is you pick any function f which is smooth on your manifold. So now n is the notation for the base manifold. So I'm working in the cotangent of n. So I pick any function on the base f, and I consider the graph of its differential. Then this gives you an example of element in L. So closed exact Lagrangian. Okay. For example, the zero section is such a closed exact Lagrangian. And more generally, if we consider the image of the zero section by some Hamiltonian diffeomorphism, so something that I can denote by phi h1 of the zero section, then this will always give you a closed exact Lagrangian as well. Okay. And in fact, there's a conjecture. Oops, that's not what I wanted. There's a conjecture which is actually very famous in the symplectic world, which says that any closed exact Lagrangian is of the form phi h1 of the zero section. So they're all Hamiltonian deformation of the zero section. This conjecture is proved in very few cases, like for n equals S1, for n equals S2 or T2, but that's all. Okay, it's a big open conjecture, but still somehow you can think that the closed exact Lagrangian is just a Hamiltonian deformation of the zero section. I don't know. Is there any question? Okay. So let me continue. So I said I would define some spectral norm, gamma. Okay. What is this? This is a sorry. This is this is given by the following theorem, which so the first version of it is due to Claude Viterbo, and then there were some generalization by many other people like Leguil and A, Matthias Schwarz, and others. And it says that there exists some distance function, a metric called denoted by gamma on the space of closed exact Lagrangian, which satisfy the following properties. First thing, the distance between, if we consider the distance between two, between the graph of df and the zero section, this is just given by the max of f minus the mean of f. Okay, so if you consider only graphs, that's easy to understand what it is. And now there's another property that if you consider distance between a Hamiltonian deformation of a Lagrangian and the Lagrangian itself, so gamma of phi h1 of L and L, then this is bounded by a quantity which is the Hofer norm of H, and which is by definition, this is the integral between 0 and 1 of the max of HT over T star n minus the minimum of HT over T star n. Okay. And we integrate with respect to T. So here I'm considering H, which possibly depends on time. Okay. Okay, so this distance has some kind of continuity like this, which is called Hofer continuity, because this norm is called the Hofer norm. Okay, and lastly, there's a last property which actually will be very important for us. It's that it is conformally exact symplectic, which means that if it's conformally invariant, which means that if I pick psi to be some conformally exact symplectic map, then the distance gamma, then it acts on the space L as it multiplies distance by the factor A, where A is the conformal factor of psi. Okay, so these are the properties of this distance gamma, and unfortunately, I'm not able to give you in such a short time the definition of gamma, but I mean the initial definition that was given by Viterbo is done with using the theory of geometric functions or Lagrangian submanifold, and then it was extended to more general Lagrangian. I mean, but yes, with generating functions, you can only define it for Hamiltonian deformation of zero section. If you want to define it for all closed exact Lagrangians, then you need Florio theory, and this is the contribution of the other list of people which is there. Okay, but it all goes back to Viterbo in 1992.
Sorry, Vincent, sorry to interrupt you. I have two stupid questions. So here the theorem, you said that you work on closed exact Lagrangians. It's just on the cotangent bundle of a manifold, or in
so in fact, so here it's really closed exact Lagrangian on T star n, just to be on the safe side. But in fact, it's possible to generalize to much more general symplectic manifold, but then it's more complicated because it's not defined on all Lagrangians. You need to be careful. And but if I stick to T star n, everything is correct. That's the...
Okay. And if I can, I have another question. So here, so you have the tube size conformally exact symplectic. If you are just conformally symplectic, you?
Yes. Sorry. Yes, I forgot to say. So conformally symplectic means that psi star omega is A omega, and then conformally exact symplectic means that psi star lambda is equal to lambda plus the differential of a function. Okay, and so it's if you're CES, then you're CS.
You have psi star lambda equal A, A lambda? No, there is
A lambda, yes, sorry.
Okay.
Yes. Yeah.
Perfect.
Okay. And for example, this is so damped Hamiltonian systems are conformally exact symplectic. Okay.
Thank you.
So it's a large class. Okay. Thank you for your questions. Okay, so there's a fact that this space of closed exact Lagrangian with respect to that metric is not complete. Actually, you should think of it as a rather weak metric. Okay, and so it's not complete. But we can, as a consequence, introduce its completion. Okay, so completion means we consider equivalence classes of Cauchy sequences, and just a metric completion of the space. Okay. Right. And the starting point for defining the Birkhoff attractor is that if we consider a CES map psi on a CES map psi, then it acts as a Lipschitz map on L, and as a consequence, it extends to the completion. Okay, just because it's uniformly continuous. And moreover, again, on the completion, it acts as a contraction. So just by the classical fixed point theorem, I'm not sure how it is named in Italy, but you will get that there exists a unique fixed point in this completion. And this unique fixed point we will denote by L infinity of psi. Okay. So you should think of this CES map acts on the space of Lagrangian and it contracts everything. And there is a fixed point, which is maybe not a Lagrangian, but it lives in the completion of Lagrangians. Okay. So now we have a problem because we are really interested in the dynamics of our map psi. So knowing that there is a fixed point in the space in this strange completion, it's not very useful, right? Because the elements of this completion are abstract object, and it's not really clear what it means. Okay, that there was a fixed point. So we need something more concrete somehow, and that's where this notion of gamma support will be useful. So what is the gamma support? So the problem is that elements of this completion are too abstract, and we want to assign to each element in the completion a subset of T star M. Okay, and this subset will somehow be the incarnation of this element in the completion. Okay, so the concrete part of this element in the completion, if you want. And so that's a definition which is due to Viterbo from 4 years ago, and it goes as follows. So we pick some element in the completion, so just a equivalence class of Cauchy sequences. And we will say that point x, so a priori x is just a point in it's a point in the cotangent bundle. Okay. And I will say that x does not belong to the gamma support if there exists a neighborhood U containing x, such that for every Hamiltonian map supported in U, then we have pi h1 of L equals L. Maybe I can make a picture. So I'm trying to define a gamma support, which will be some weird set like that. Okay. And instead of defining the gamma support itself, I'm defining the complement of it. So I'm defining what it means to not be in the gamma support. And we will say that a point x does not belong to the gamma support if there exists some neighborhood U such that each time I take a map supported in U, then it acts trivially on L. Okay. I think it's a natural way to define something. But of course, so maybe you may wonder what it means here to act on L or not, meaning of this. So you know, phi h1 is Hamiltonian, so it's it's, if you want, it's conformally symplectic with a factor 1. So for H1 acts, let me go back to that. Okay, I'm going back to this property here. If we pick a Hamiltonian diffeomorphism, then we are in this situation, but with A equals 1. So phi H1 acts as an isometry on the space of Lagrangians. And so as an isometry, it will extend to the completion. And this is the meaning of this. So now maybe what I can write is that phi H1 acts on L and extends to the completion, just because it's an isometry on this on this space. Okay, I don't know if there is any question. I will give some properties of the gamma support next. Okay. So here are the properties. The first property is that if we start with some with an actual Lagrangian submanifold, I mean smooth Lagrangian submanifold, so an element in L, and if I compute this gamma support that was defined by the Viterbo, then I get the Lagrangian itself. So, okay, so if I start with some just a standard smooth Lagrangian, then the gamma support of L is the Lagrangian itself. So somehow it makes it a good definition. Another remark is that this is invariant with respect to action of CES maps. If you start with some CS map psi and compute gamma support for psi of L, then you get psi of the gamma support. So it's really well behaved. Invariant. I have a long list of properties. And so if next some intersection properties, so maybe you know that let me write it here. It's known that if we pick L and close the exact Lagrangian, then L should intersect all cotangent fibers. My base manifold is back to M. Sorry. Okay, so the closed exact Lagrangian should intersect all the fibers. So if you see the fibers like that, then it should intersect all of them. And somehow we have the exact same property for any gamma support. Okay, so the gamma support should intersect all fibers. So in some sense, it tells you that it cannot be too small. It's always it's at least dimension. Well, at least intuitively, it's at least of dimension n. Okay, you could intersect all fibers. It has also some nice continuity properties. For if we have a converging sequence of Lagrangian with respect to that metric gamma, then we know that the gamma support will be included in the limit of the gamma supports of LKs. Okay, so it's some kind of lower semi-continuity or something like that. And something that I won't be able to explain in detail, but the gamma support is coisotropic in some generalized sense. Maybe I should put some quotation marks here because it's coisotropic. I mean, it's not always a smooth manifold, so it maybe not very clear what it means to be coisotropic, but there's a generalized notion of what it means to be coisotropic, and the gamma support is coisotropic in this generalized sense, always. Okay. And there are some examples where it's not Lagrangian in the sense it's higher dimensional coisotropic submanifold. Okay, and something. So all those properties are in the initial paper of Claude, but something that we proved with Marie-Claude and Claude is that, moreover, if the gamma support is compact, then we may consider the map from the cohomology of M to the cohomology of U for any open set that contains the gamma support of L. So that's the map induced by the projection on the base, right? Maybe I should write it. It's the projection on the base. And this map is always injective. So this tells you that the topology of any neighborhood of the Birkhoff tract, of the gamma support contains as much is as complicated as the one of the base. Okay, that is cohomology of the neighborhood is as big, at least as big as the one of the base manifold. And the last property I wanted to give that, which is due to Asano, Guillermo, Ike, and Viterbo, is that if this gamma support is compact, then in fact it's connected. So under this compactness assumption, we know quite a bit about the topology of this gamma support. Okay, these are the main properties of the gamma support. And okay, now I will be able to define the generalization of the Birkhoff tractor now. Do you have? I think I have something like 10 minutes, right?
Yeah, exactly.
Okay, great. There's a remark here saying that in fact this gamma support can also be interpreted in the language of microlocal shift theory. I just wanted to make this remark, but I won't say much. It just somehow it's a way to it tells us that this is the right notion somehow, because it can be defined with different approaches, and so I think it's the right notion to consider. Okay, so now let's go to the generalized Birkhoff tractor. And so now recall I said that if we pick some CES map psi, then it acts on the space of closed exact Lagrangians. And I explained that there should be some unique fixed point in the completion of the space. And so we have an element in the completion, we can take its gamma support, and this object I will denote by B tilde of psi. Okay. And we prove that when we do this construction, in the case of where n, the base manifold, is S1, so in the if you want it, in the classical case of the Birkhoff tractor, then we recover exactly the classical Birkhoff tractor. Okay, so this B of psi is the classical Birkhoff tractor from almost a century ago. Okay. And so as a consequence, this construction here, the gamma support of the unique fixed point, we will call the generalized Birkhoff tractor. Okay, that's what I just wrote. And so then I can just use the properties that we had before. So so for any conformally exact symplectic map, we have this map, this set B tilde of psi, which is a closed invariant subset of psi. and which is connected if it is compact. We know it intersects all fibers. We know it's coisotropic in some generalized sense. I mean, all the properties of gamma supports are true for this invariant subset. Okay, but maybe that's the sort of takeaway result. If you want to keep only one thing from my talk is, yeah, we are able to associate to any conformally exact symplectic map a closed invariant subset with a lot of nice properties. Okay. And yeah, so in fact, maybe that coming back to your previous question, Anna, so in fact, this can be generalized to more to other manifolds. So for example, Liouville manifold, we can also define a subset of a similar form, but then the distance gamma is not defined on the space of all Lagrangians. There are several possible metric spaces. And depending on whether the Lagrangians are equivalent or not in the Floer theoretic sense. And so that makes everything slightly more complicated, but a lot of the story can be generalized. Okay, so now given the time I have, I could either explain why we recover the classical Birkhoff tractor, or maybe I will just jump to another a property that has the Birkhoff tractor. So let me skip the proof that we recover the classical Birkhoff tractor. You see, it's not very long. In fact, we're just using all the properties of the metric gamma and of the gamma support. And I just want to spend a few minutes to explain the connection of this construction to the discounted Hamilton-Jacobi equation. Okay. So we pick some Hamiltonian on the cotangent bundle, and we consider the following equation. So alpha u of x plus h of x dxu equals constant. And this is called the discounted Hamilton-Jacobi equation. And here the unknown is the function u, which goes from n to r. Okay, so we want to find such functions u. Okay. So in fact, so this is related to conformally symplectic dynamics by the following fact, is that if we pick some function u, then it will be a solution to this equation if and only if the graph of the u is invariant by the damped Hamiltonian flow. Okay. So solving this equation will tell us something about the dynamics. But okay, and there's some work by Lyons, Papanicolaou, Varadan in 87 saying that if we pick alpha, so alpha is this factor here, to be positive, then the discounted Hamilton-Jacobi equation has a unique viscosity solution. So it's some kind of a weak solution. So in general, there is no smooth solution, but there is some weak solution, right? And what we proved in this context is that if we assume H to be a Connelly Hamiltonian, so this means that H is convex in the fiber. So this means H is convex in P and superlinear in the fiber in P. So that's somehow it's the case that we have in classical mechanics. And then for every point where this viscosity solution, which is almost everywhere differentiable. So at every point where the derivative exists, which is almost every point, then we know that the differential should belong to the Birkhoff tractor. Okay, so the B tilde that we defined with Claude and Marie-Claude. And yeah, so just a remark is that this result is wrong in the case H is not tonally. There are some examples which are due to Maxime Zavidovic. And yeah, there are just like maybe two ingredients in the proof. I won't say much, but two ingredients in the proof of this theorem is we need the notion of graph selector for Lagrangian submanifold, and we also use ingredients from weak KAM theory. Okay, and so now just before I conclude, maybe I should say that after the talks of Olga and mine, maybe there's a natural question to ask after those two talks, which will be what can we say for higher dimensional billiards, dissipative billiards. I mean, is it possible to generalize the result of that Olga told us about, or not? I don't know. I have really no idea, and that's maybe question for the future. And grazie mille.
Thank you a lot, Vincent, for a great talk. Enjoyed. Are there any questions or remarks?
Yes, I have a question. So thank you very much, Vincent. Which is I think there is a simple example to visualize that the gamma support may be different from points cannot be inside the Lagrangian, no? Points in the gamma support, the example of the segment, the extremal of the segment, which is the idea to visualize some example where
Okay.
the gamma support and the Lagrangian.
Okay, so I'm not sure if I gave enough information on gamma to explain everything, but
okay.
I can try to
give the dynamical idea if you wanted to.
Yes. So no, for example, if when we consider the classical Birkhoff attractor, you know, first there is this Conley attractor which looks like this. I don't know. And then when we go to the Birkhoff attractor, we cut those parts, right? And somehow we know a priori that this part, which we could call the hair of the attractor, at this extremal point, it's not coisotropic in the generalized sense. So somehow we know that it should not be here in some sense.
Okay.
I don't know. So that's maybe one piece of intuition. Another piece, maybe for people who know the notion of capacity, my intuition is that, for example, if I consider a segment in the R2, and then I can contract the segment with something which has zero energy in some sense. Okay, so somehow I know that I can do it with arbitrarily small gamma, contracting a segment. So I know that somehow a segment like that should not be seen in the gamma support, because it doesn't count. It's not seen by gamma. Okay. While if it's a closed piece of Lagrangian, then I cannot contract without with a arbitrarily small gamma. That's the rough intuition.
Okay.
And, so I know that what remains is basically the part which looks like a closed curve, and that's the.
Okay, thank you.
Are there other questions? So I have two questions. For sure, stupid, sorry. So you said that there is result by Asano and I don't remember that the fact that if the gamma support is compacted, then it's connected.
Yes.
So that you can apply. So do you have examples where you have dynamics where the Birkhoff attractor, so there should be like the gamma support or something, is not compact or not connected?
And not connected. I think yes. I think actually Marie-Claude explained us some example like that. You were there recently.
Okay.
But wait, let's see if I can remember. Yeah, I'm not sure if I will be able to remember in. I can't find it on top of my head right now, but it's not very complicated. But
I think it's outside the general cotangent bundle.
I think it was in anti-star one, except that it was not. But it was not. But it's just we are not in the case where there is a compact Conley attractor. So
Was it related to the
part of the dynamics go to infinity and
when you have like something like that looks like you have the zero section, then some hyperbolic points there with saddles that have some unstable manifold
something like this.
that goes to infinity, and then you add lots that you have some something that looks like I will arrive something like R plus times
Yes.
okay. Yeah, okay, sure, sorry.
Something like this.
Yeah, indeed, it should be like that there you have hyperbolic points, but then you cook up something. But I know I have a terrible memory, so I don't.
Yes,
something.
I'm also.
Okay, no, but just okay.
confused now.
It
I'm
exists.
sorry.
It exists that okay. There exists example. Okay,
Yes.
perfect. Okay. And so if I can, I have another question, unless there are other people with other question. I don't want to take all the place. Okay. So so in the case of the Birkhoff, the standard Birkhoff attractor in T-star S1, there is this criterion of Charpentier about say something about the say for example the fact that it's the Birkhoff attractor is topologically complicated. Would you expect some? So I think that there is
Yes.
is there something in the higher dimension, or could you expect something in?
Yeah, I don't really know. So Olga defined these upper and lower rotation numbers in the Birkhoff attractor, and then we know that if they are different, then we know the Birkhoff attractor should be complicated. I mean, at this point, I don't know how to define this generalization of these rotation numbers. I didn't think much about it yet, but I don't really know. Maybe it's possible to define some kind of a rotation set, and then if this thing has interior, then maybe we can deduce something. That would be the hope, but I don't know.
Thank you.
It's related to that question.
Yeah.
Higher dimensional billiards.
Thank you so much. Are there other questions or comments? So if not, let's thank Vincent again.
Thank you.
And so let me thank Olga and Vincent for the great twin talks. And I think that's all for today. So